I'm fine with this, The rocks being an the demonstration. What was it? Mm-hmm. Check it. Oh, no, who said was happening. Yeah. Good evening, class.
Good evening, Doc.
Yes, I trust we are doing well. You're welcome.
Thank you.
Yes, Doc, please, we are doing well.
Okay. All right. So today we are continuing with our course in rock mechanics. And just before we continue to any other thing, if you have any comments on what we covered yesterday, you can bring that up. But I think I will allow some 10 minutes. I think someone approached me. He's one of the candidates here in this class. He also said he has some presentation to do. So I will allow your class rep if he's around. Engineer Tracy, are you there?
Okay, I'm here, but I'm driving to the house, so give me some few minutes. I will get back.
You did what?
I'm driving to the house, so I'll alert you when I get to the house.
And as I can.
Oh, Doc, within.
Oh no, that might be after my class because once I start, no.
Okay, so after your class, give me some
Mhm.
5 minutes. Or thank you.
All right. Okay, so who can help us recap what we did yesterday? Then we can continue. Any recap? Help us recap what we did yesterday. I have a very interesting name here, Scriven. You didn't hear me do.
Yes, Doc, I'm here.
Oh, okay. But actually, you reached it through and Scriven and started. There, guy.
Well noted, Doc.
Okay, so what do you remember from yesterday's lesson?
If I recall, we made mention of and we defined what rock mechanics is, and we showed the variation between rock mechanics and that of geology, and we define what rock mechanics to be whenever stresses, external stresses they are imposed on any material, the response that the material tends to give out is what we define as rock mechanics. So we came to also give the various aspects of it, where some materials are as a result of man-made activities, like the concrete we use for the building, because they are man-made materials, they have the continuous, homogeneous, isotropic, and the linear elastic features or the properties. So we can talk of having a homogeneous material because we can be able to define a proper ratio to which they are mixed up. Like maybe 1 trip of sand, we are supposed to use half bag of cement and this volume of water. Then we talk of the isotropic, the linear elasticity. Then we came to make mention of the rocks. And we say that rocks are made up of minerals. And because the minerals, they may have some aspect of structural deformation, which is inherent within the rock. You cannot have a homogeneous system within a rock unit like the man-made materials. So we came to define the Chile for the man-made materials, and for the natural occurring rocks, we came to have the DIAN, which can be the Dyna or DNA, as you said. So that's what I learned from the lecture yesterday. Thank you very much.
Beautiful. Class I say a passing on every class in the moment. Class rep, what do you think?
Doc, please come again.
I say a passing on OJ class. Oh, that's beautiful, Scriven. You did a good job there. Who else
Thank
has
you very
something
much.
to add?
A lady, one from a lady.
Yeah, exactly. Hi. Lovelace, are you talking? We can't hear you. Who can hear her? I don't seem to hear anything.
Hey,
Okay. I saw some ladies' name popping up yesterday quite often. Sylvia was one, and Portia. Where are you?
Sylvia, come and talk.
Doc, we are here. Today we are observing.
I'm sick, oh, my mouth is sick. I can't talk.
Okay.
Today, Sylvia and I, we are observing.
Craven has said everything.
We learned about Chile and Dinah.
Yes. Diane and Chile.
Yes, yes.
Okay.
That the natural rock can be discontinuous. That means it's not maybe in a continuous way. You can find some at the top and you go and find some at the down. And it can be homogeneous and anisotropic. That means the strength can be determined and non-elastic. So that's as it's on the screen. Thank
No
you.
Portia, thank you. All right, so that's it. Today we are just I think we got to a slide like this where I was showing you how a typical rock mass will look like together with all of its various discontinuities and all the other things that we talked about. Of course, there are some that you cannot look at a rock mass that is accessible to you to determine these, but unless you have gone to the lab to conduct certain tests on them, that is when you'll be able to see some of these features that we are talking about. And so we move on to our next slide. So this is also a typical image of an accessible rock. That is, if I have any rock mass that is exposed, such that I can get close to it and examine and see what the properties are. So now, once we are talking about rock, we've talked about how it behaves and all that. It'll be very interesting for us to get to know some of its the uses of it. So can anyone help us mention some of the uses of rock? So you tell me one, we move to the next person. So who will start? One use of rock.
Doc, for construction.
For construction, you see, that is the issue. Assuming I request for 15 and you say construction, what can you now? You get the point, because
Yes.
there's a lot within the construction. So if you just say construction, oh, you've
Uh,
lost the rest of the mark. So be specific. Yes.
How will I say it?
Doc,
Yes.
The use of rock for
Uh-huh.
one, road construction. They use boulders for dam construction. For
Doc, for filling routes and
For
other muddy
filling.
places.
Good. Mount machine.
Okay.
Doc, for concrete works.
Thank you. What else?
Doc, for
Doc, for
rock
manufacturing
base,
of tiles.
aggregates for rock base.
Thank you. What else?
Aggregates for
Doc,
road base.
cement
Aggregate
manufacturing.
for.
Road base.
Okay, yes, for road base.
Yeah, Doc, for water treatment.
For water treatment, thank you.
Doc, for
For
erosion
cement
control.
manufacturing.
So
Slope
is it?
stabilization.
Thank you. Who else?
Doc,
Cement
laying social foundation.
manufacturing.
Tuari, can you come again?
Laying social foundation, Doc.
Okay. Who else?
Cement manufacturing.
Cement manufacturing. Good. Who else?
Slope stabilization.
Stabilization of roads.
Doc, also as tourist site attraction.
Exactly. And then sea defense.
Yes.
So you've
For
done
medicinal purposes.
good. So you see, you've mentioned a lot. So the person
Doc,
who
construction of mine openings.
good.
Doc, agriculture.
How?
Habitat for resources.
Habitat for
Doc,
resources.
agriculture.
Agriculture. How? That's what I want to know.
So in agri, we add to the soil to reduce acidity. We add some rocks to the soil to reduce the acidity, like the lime rocks.
Okay. Good one.
Nice.
Doc, some rocks can be turned into useful metals.
Beautiful. Good. So then,
The preparation of
sharpen knife.
nice one. So thank you so much. It means we have various uses for rock, and then we have been able to exhaust almost everything I have on this slide. So we move on to the next one. So the next one is looking at the economic benefits of rock. Who can state some of them? Mineral. So we obtain minerals from rocks. Which other thing can you mention?
Tourism.
Tourism. We earn money from that. What else?
Aesthetic. Yes.
Doc, sea defense.
Sea defense. We are looking at economic benefits, importance.
Mineral extraction.
Mineral extraction, which we sell and then earn from it. What again?
Quarries.
Energy production.
Energy production.
Doc, you can use that dimension that can deploy surfaces for foreign exchange and other household sensitive. Foreign exchange. Good.
Job creation.
Jewelry.
Okay.
Jewelry.
So, jewelry. Good. So we are looking at the various rock types that we can use for varying things, like someone mentioned, for its beauty, the beauty of it. Okay. And then we have
Doc, can I say something?
yes,
It
carry
also
on.
determines the financial ability of that is geographical area.
Yes, it's true. Good. Then sometimes when we extract minerals from it, we can sell these and then earn royalties as a nation from it. All of these things are economic benefits. It provides us with some employment, just as many of us, for which reason we are inside this class now. So these are some rocks, granites being crushed into finer aggregates for juice. These are other juices of rocks. So you see them, there are many, tons of them. So now this is also a slide that is just showcasing the various nature of a typical rock, which we talked about. And I think I didn't mention this. So those of us who are new to this word, when we say something is in situ, it simply means it is in its place, in place, okay? In place. So when I have a rock material and it's in its original place, it will exhibit certain behavior. And when I narrow down into that rock mass in its original place, I will be able to see exactly the portion of the rock that has no discontinuities. And that is what we can term as the intact rock. So when you are far away, okay, from the rock material, or you are looking at a larger view, a larger area of the rock material, there are so many features you can see. Please mute yourself if you are not talking to us. So if you are looking at a wider view of an excavated surface, you will be looking at all these properties, the physical properties that defines a particular rock material. You will see them. But as you narrow in deeper and deeper, you will be able to single out certain portions of the rock that has no discontinuities at all. And so when you look at this image that we have here, you realize that the item number 5 has got a lot of discontinuities, which you can see. When you narrow down, you see them quite spaced in that order until you get to a portion of the rock where it has no discontinuities at all. And it is that portion of the rock we usually will more or less carve or cut our samples out of and use in the lab for testing. Reason being that if we use the excavated portion as in the wider surface area that has got all the various constituents of the rock property, and we test in the lab, the tendency of us not getting the true strength values of that particular rock material is high. And so if we want to make any engineering decision and we have to conduct certain laboratory tests, we always do prefer that we narrow down onto a portion of the rock that looks quite smooth, devoid of all of these. Of course, with the anisotropic behavior, we cannot determine that by way of looking at the smoothness of the surface. But if we want to test, some of the physical things we have to avoid is the discontinuity. Why is this so? Because if a rock material already has got, if the rock material already has got certain features, okay, cracks on it, as soon as you exert your load onto that particular rock material to test for its strength, because there's already a crack on the rock material, it is going to slide or fail along that little crack you have there. So in order not to have any of such influence on the strength and the true behavior of our rock material, when we want to conduct laboratory tests, we prefer the intact rock material, the portion that is devoid of discontinuities. So then,
Hello, Doc.
yes, carry on.
And please, can those discontinuities affect drill and blast?
Yes, the discontinuities, they play a role when you, and to avoid the impact of it, that is the more reason why we prefer to know the true nature of the rock, either than going for that aspect of the rock which has a lot of discontinuities. Because if you have a rock that has so many discontinuities, what are some of the things that might happen? You will throw your blast, and some of these explosives and other things, the gases will escape through some of these cracks. And at the end of the day, the amount of energy you are expecting to have this explosives exert on the rock to get certain fragmentation or fragment sizes, you may not have that. And so it is possible that these discontinuities can affect your drill and blast activities.
All right, thank you, Doc.
So we move on to our next. So what are some of the things that can define or determine the strength of your rock? So the very first one is mineralogy. So the various minerals that we know of, or the element we know that exists. For example, if we mention the first 20 elements and all that, if we mention some of these elements or the minerals, every one of them have got certain peculiar features. And it is these features within them that give us the various types of bonding that exist in material. And so when I have an element or a rock material that is made up of some of these minerals that are already competent by nature, if such minerals are coming together to form a particular rock type, then of course we need to be certain that we are going to have a very competent rock. So in this sense, what we are saying is, depending on the type of mineral that we have that is making up a particular aggregate to give us that rock material, the strength might vary. Then we have the mineral assemblage, how these various minerals came together. Of course, sometimes due to their orientation, whether they are rounded or whatever, their assembly can also influence the strength of your rock material. And then their particle sizes, are they finer? If they are very fine, at the end of the day, it gives you a very solid rock, free of so much void or empty spaces within it. And so the strength of the rock is enhanced when you have finer particles. Then the shape of these minerals. So you remember I mentioned we have, during the cooling processes of these to get rock materials, or how these aggregates come together, they may be crystals, which means they are very fine and they have definite shapes. And then they can also be formed in a form where you cannot even determine what shape it is. And so we just use the English word irregular, right? So, and then in the geology terms, we say they are amorphous. So the shape of it can also affect the strength of the rock. Take, for example, if I have a rock that has got sharp edge like this, the slightest impact, it will break. In the same way, if I have one that is quite rounded or robust enough, it can also define the strength or the competence of that given rock. Then again, we have our next thing, which is the type of bond that exists, whether the bond is as a result of cementation that is bringing two entities together, or it is the inherent, the cohesive bonding that exists within the tiny particles themselves. So depending on that, so let us try to see if we can, let me use an analogy to see if this is possible. So take, for example, this solid tape. If I bring this device and I put them together, okay, and they get stuck to each other, what is bringing them together, putting this red against that, is what we are terming as the cementation, because there are various entities that are being bonded as a result of certain external things. Then we also have another type of bonding that can exist as a result of cohesive forces that exist within the substance, which means this as an entity already has got certain features, adhesive features that exist within it. And if this also has got the same adhesive features, and it happens that they are able to bond without a medium, but rather it is as a result of their inherent properties that is bringing them together, that is the type of bonds that we are talking about here. So it could be cementation or as a result of cohesive forces. Then we have the presence of discontinuities as one of the key things. So if I have a rock material that has got cracks all over, it can fail. So as soon as I want, let's even take, for example, this device I have now. If I want to compress on this device to check the competence of this box, because of this line that is pre-existing along it, the moment I exert the force, it will try to look for the easiest path to cause the failure. And so you see that the sliding will just occur, and then you will judge that this is the competence of the rock. But remember, you cannot bring the entire mine to the lab to test. And so you are using just a representative. Sometimes you have 20, 30 samples, and you bring these samples to the lab to come and test. Sometimes 14, 9. And you are testing this to use in your decision making to judge what you think the rest of the rock mass you are dealing with in a particular zone or area is. And so we have to be careful not to bring materials or rock samples that already have got these pre-existing failure. Else you will record lower values, and when you want to continue to mine, you will end up making decisions that are stringent, which will mean more money. And as geotech officers, you don't bring money. Your decisions help to bring the money, but then you will always take cash with the motive of trying to augment safety practices in the mine. Then our last one is the presence of water in the rock voids. The presence of water. So take this. One of our enemies, okay, as geotech officers is water. Because water has that tendency of losing the bonds that exist within the aggregates that formed a particular rock type. And so we try as much as possible to be away from rock. So it's just like you being in the glass. You don't want to be playing with stones. Okay, so you know that this is the nature of your rock, and these are the behavior or the type of rock you are dealing with. And water is one of the major things that can surprise you at any point in time. You can go and inspect an excavated space, there's nothing wrong. But then maybe the next day you go and you have a rock fall. It could be as a result of stress. It could also be as a result of some water finding its way, seeping, maybe as a result of some rainfall, where you have surface runoff finding their way to collect within a particular space. At the end of the day, you see this water dripping all over. And so when you have this particular situation, you can be disappointed. And so water is one of the key things that we do not want when we are making some of these decisions. And so you must know them. Try to find out whether there is water and at what quantities they are present at a particular area. And hence the role of the dewatering team in your mind. So we are moving to our next phase. I think we should have ended here yesterday and we didn't. So we are moving on to the next phase, and with the next set of slides that we shall be looking at, I want us to look at how rock mechanics programs are being implemented, what goes into it, and then the field application of rock mechanics, which I've already mentioned a few, and then try to understand
Doc, I have a question.
Yeah, carry on.
Doc, I want to know the difference between the mineral assemblage and the type of bond and yeah.
So mineral assemblage here could be if I have different types of minerals, okay, coming together. Maybe I could have a particular rock type. Let's mention any elements in the periodic table coming together to give you a particular rock type. Remember, we said there are certain rock types that come together as a result of molten magma or whatever that have transformed to give us a particular mineral. So if I have a particular rock sample where I have, let's say, it's a dolomite rock, I have calcium present in there and I have sulfur in there. All of these are minerals that are coming together to give you a particular rock type. the way they are assembled, the type of minerals that assembled to give you that rock type can affect its strength. That's what we mean. And the type of bonding here is, once I have got that amalgamated type of rock with several elements or minerals present, that is now one piece of rock. And I have a different type of rock that is also formed differently. And when they come together, that is bonding. Okay. And then
Okay, Doc.
Are you clear now?
Yes, I think I'm okay.
Good. So then let's see this one. And I said we would then look at what we call index properties of rocks. And this is where the game will start. Okay, into our calculations. So the engineering problem posed in all structural designs mainly is the prediction of the performance of the structure under loads. Okay, that are being imposed on it during its prescribed functioning. So if I say there's a problem, what is that engineering problem? I am trying to look at a particular design. It could be the stope you have done, you designed. It could be your benches you designed and told us we should excavate the space like this to have our pits. That is a structure that you have designed. Okay, so the problem here is us trying to find out, to determine, predict how well this particular design you have proposed. So as an engineer, you are trying to see how it will perform. The design that you have proposed is going to perform in the presence of your excavator on that bench, excavating day in and day out. The blast you will be throwing on another side of the pit. And then the various activities going on with the dump trucks. These are the loads we are talking about. So we are trying to predict the performance of a design under all of these circumstances. And the moment there is that trigger, you won't sleep. You will want to find out. So a problem has arrived. You will then want, as the geotech officer, want to do your various investigations to find out why. So rock engineering is concerned with the applications of the principles of engineering mechanics to design the rock structure generated by mining. So now, once you have studied your basic mechanics and strength of materials and all the pure mechanics or the pure sciences there, you then come and apply them to certain principles and theories. That is rock mechanics. You then go to the field and you want to now show your jump agency. You now want to interpret what you have studied or what you are going to do now in this class, translate that to the field and apply and make decisions with them for us to clap for you. That is rock engineering you are doing now, which is similar to applied rock mechanics. So rock mechanic principles are fundamentals to mining engineering. Since the excavations that we create, okay, the excavation created changes the force fields. What does this also mean? So take, for example, I have a whole surface. Just before we started our mining activity, there are forces that exist within the material. But because there was no disturbance, they had already balanced themselves. And that is giving us what we call equilibrium. They are all in their original forms. Maybe their net are all zeros. The strength, this has balanced the other, and they are all okay. But the moment we go there with our intention to explore for mineral, we send our excavator and then we exhume material from this surface. What do you think has happened? The moment you do that, you have disturbed the system by way of taking out material. And what is happening now is that you have created an empty space. And remember, each of the particles that was present here was helping each other to maintain equilibrium such that there will not be any failure. So the moment you take this out, you have created a void, and all the stresses that these other materials were containing will have to be redistributed within the entire system to ensure equilibrium. And the moment that fails, that is where you will have your stope coming down or your wall sliding over. And so, because we want to look at this and find out how we can resolve some of these issues, hence we have to study rock mechanics, apply those principles to our mining engineering things, where we think that our excavations that we are doing will be causing disturbances to the various force fields that exist within the rock in its physical environment. So if I want to implement a rock mechanic program, how do we go about it? So to implement a rock mechanic program, it goes through phases, 5 phases. The very first one we term as site characterization. The next we call model formulation. The next is design analysis. We have the rock performance monitoring, and then we have the retrospective analysis. So we'll take these one at a time. So when we get to the other slides, we can brush over. I'll explain them here. So site investigation, what is it then? It's just like you trying to set up a business. Then you go out there to find out, will this business be lucrative? Will people patronize it? Who are the people that will be interested in this thing I am trying to propose? Okay, so when you do that, studying the market or doing that market analysis, you are doing the site characterization. So you are bringing all the various entities and properties that you think will favor the idea you have got. And that is your site characterization. So translating this analogy to your rock, you want to mine. And so during the very early stages where the diamond drilling is going on, we drill and we don't throw away the rock sample. We pick these things up, take them to laboratories and test. The geologists will also be around to characterize. Together with geotech officers, help us characterize the various properties that we've seen. So assuming I drilled this depth, once the core is out, we begin to examine and study. At what depth did we see a crack? Is this crack going to extend to the north side or the west side or what? Or is going deeper? You want to investigate. All these properties will be gathered. And that defines the various types of rock that you have. Then you move to the next location. You do your drilling again. And then you see, are the rock types I found within this first drill hole, is it the same as the one 500 meters away or 300 meters away? So you bring all of these things, together, okay? And once you have them coming together, you have gathered enough data on your rock. I've seen someone ask that, can we term that as feasibility studies? No. Site characterization is different from feasibility. Feasibility, you are looking at how plausible the business is. Okay? You want to see all the elements, the economic value of what you are doing. That is the main focus of a feasibility studies. Of course, when you want to do them, it encompasses so many things. But with this specific thing we are terming as site characterization, you are gathering data about the property of the rock. It is out of this data you have gathered that will inform you on what step to take, whether you should go surface mine, underground mine. If it is an underground mine, will you use the shaft approach or you are using a decline, depending on the competency of your rock? So how wide can I open my stopes? All of these things will be as a result of the site characterization, the data you will gather about the rock. Then the next one is now trying to conceptualize the data, make sense out of that data you have gathered. So you now want to see how reasonable is this? What can I do out of this? Trying to come up with models and all that, prototypes and all these things. At that stage, that is what you are doing. Then here, you then use softwares, which you will feed into your model, bringing in the computational softwares like the rock science, okay, the rock science packages that are available to you, the Flag 3D, the Plazas, and all those other softwares that are available to you. You then want to feed your system. That time you had already done certain prototype modeling to take a look at how your whole system will look like. Now you are feeding that data, mimicking the prototype into a software to see where do I have stresses more if I do my excavation this way. If I make it wider, what will happen? Okay, let me close in. So during that phase, you are doing the design and you are doing the interpretation, making use of your maths analysis and math methods and all those other things that you've done. Of course, at that phase, someone has used these mathematics to design a model for you. So you are just implementing. All you need to do now is to be able to more or less communicate the outputs that these softwares will give you to your stakeholders. We move on to the next phase, which we term as rock performance monitoring. So remember, diamond drilling is very expensive. And so you may not have enough data to touch on all other aspects that you would have. So, but you have gotten enough that you can start something with. And so that means the job has not ended as a geotech officer. So as soon as you have given your advice that go ahead with your designs and let us start mining, you then will not sleep. You go every day based on the prototype and the analysis you did in the model. You go there and check how is the northern side of this excavation being affected as a result of the machineries that we are using. How is the southern part responding to the various blasts that we are doing? It could even be said that you are using certain drill diameters or whatever, but then management is saying, oh, we want to increase production, so let us increase the number of holes we can blast at this position. Because you did your calculation based on certain parameters. Now, once they implement it, you want to go and see, has anything changed? To gather more data to feed into your model and make future inferences. Then we move to the last phase. And at this phase, what you are interested in is to do back analysis. So that's why when you throw a blast, you will see your geotech officer coming there every morning, as if they have an ATM machine on the wall. They come every morning and be looking around, inspecting every place, because they have an idea where a fault is lying on the wall, where they have discontinuities, they know. Where they have folds and various rock types that are weak, they are aware based on the site characterization data they got. And so at this phase, they are gathering more data and then feeding that data back into the model and trying to see if they can refine this thing. But then what I've realized over the years is that most of the mining companies, once they get the very first few data, yeah, the boy it's like a chart. Oh, our granite at this site is having 25 megapascal and one. Okay.
Now we have changed.
You have changed there.
Yeah, we are using radars and other instruments to monitor the walls.
Yes, that is there. That one is fine. But we are talking of the radar and whatnot will not give you information on what decision we should take in our blasting. Because when you do the testing, the data, the values of the rock is what you feed your drill and blast team with. That the rock has this strength properties, and that is what informed the bedding and spacing that the blast engineer is using.
Yes, so Doc, with that one, we have what we call the field mapping.
Okay.
And also the core logging. Do you get it? So with, as you said, with the site characterization and the model, with the field mapping and the core logging, it will at the end of the day help the geotech team to come out with a model. So they will give that model to the drill and blast people. So they will know that from the top, we are starting from the ore side. So we can open up the bedding and the spacing. When we are getting to the other section, we are going to transition. So we reduce it to the fresh. So that section, mostly it depends, unless we are going deeper, then we also continue doing other drilling with geotech and other stuff, so that they can also advise the drill and blast team on how to go about their patterns and other stuff. So before you release any patterns for survey or any operations team, the geotech chief need to sign. You need to, at the end of the day, use that patterns through some system and sign or accept before you can release it out. If not that, he can decide to reject. There are a lot of instances they have been rejecting some kind of patterns. Advise them, open up, close up. Sometimes you can, at the end of the day, they have some patterns they can call geotech patterns, meaning looking at the western side of the wall. Let's use this kind of patterns. If not that, I won't accept you people to drill or blast. Thank you, sir.
Thank you. Thank you for that wonderful contribution. So you see, once you have picked the data at a point in time, it's not enough. You have to continually, and that is this phase we are talking of, the performance. It is the performance, rock performance phase that helps you to keep gathering information, keeping more data, gathering more data, and that is what you will use to advise subsequent activities of the mine. And so you may want your tons to go up, but the geotech officer would also have a different opinion. And here you have to defend and defend and defend and defend. And where you fail to defend appropriately, yeah, the buyaka, and then it happens. Who was the geotech officer? Couple, you are in trouble. Although at that point you cannot just say semi-kind. You can't say that. I told you people. Yes, you told us. But what did you do? Okay, so these are the 5 phases we go through all the time as geotechnical officers. And I think at this point we could have even ended the course here, because everything else is on this. Or what do you think? If it's me, I try test. No,
Yeah, so let's finish.
Okay, so having done that, I think I've explained all of these things. So we are here. What are the objectives of a rock mechanic program or rock mechanics? Why do we need to study rock mechanics? So irrespective of the excavation technique that you are adopting for your ore extraction, it is possible, okay, for us to come up with 4 key things that will direct us. So the very first one, why we do rock mechanics, is to ensure the overall stability of the complete mine structure, that are being defined by the ore sources. So the stability of the entire structure that we have is our core goal. And these things are being defined by where is our ore? Where have we mined and created empty spaces? What is the nature of the adjacent country rock that are present? So you are focused on overall stability, taking into account all these limbs. Then the next one, it's your duty as a geotech officer to study rock mechanics and help us safeguard all our major service openings throughout the designated life of the mine. So if we have created a portal where we enter a decline, we are expecting that so long as goldfields stays, So long as Trano mine is there, that access route we have created should stay there because it is our main entry point into our production phases. We don't expect that we finish and tomorrow, once we get in and we come back the next morning, it's closed or collapsed. So it is your job to protect that. The next one is to secure access to safe working. Okay, provide secure access to safe working places in and around the centers of all production. So if we are on level whatever and we are working, we are expecting that once we go in there, we should be able to come out. We don't pass and see rock fall. How do we come out? Is it Chile or so some time ago? So you have to provide us with secure access to safe working places within and around the various centers of production. Then as you do this and take these decisions, giving overall stability, protecting the major service openings or whatever, and then securing access routes for us, one of the key things is that you have to safeguard, preserve areas that we are yet to mine in the future. It is your duty to ensure that we don't take certain decisions that will affect areas we are yet to mine. Else we go there and then we cannot mine. And so as part of your duty, you are to help preserve mineable conditions, okay, of unmined areas. So the applications of rock mechanics, we want to determine the physical and mechanical properties of rocks. These are some of the things we do. We investigate, okay, investigation of the condition of the stability of the area. So every day you are there on the field. You don't leave your job to national service people or internships. If you do that, they will go and bring you 23 point whatever as 32. Okay, 23 as 32. You'll record it and use it for your records. Of course, if you do that under supervision and you have foresight of what is happening, you can always detect for outliers and whatnot and make proper decisions. But where you relent on your job, at the end of the day, you will mess up. Then you study rock pressure and its occurrence in opening. It is your duty. Then study the subsidence, rock subsidence, and the effect of the opening. What is the tendency of getting subsidence in the mine that you are in or that opening you have created? And then to study the presence of, okay, the processes of fragmentation of rock during excavation. So you visit the phase when excavation is going on to see what is actually happening. It can give you an inferred idea as to what to do. So, how do we resolve rock mechanics problems? The very first one is through experimental methods, okay? Experimentation. So we observe by observation of the behavior of our rock during the production stages. We do observations and then we make certain decisions when we get to the office. You can also go there and then look at the behavior, okay? We do certain tests which we term as the physical and mechanical properties of the in situ, the rock that is in place. We can conduct certain tests there on site. Again, we can determine the physical and mechanical properties of the rock when we take certain samples of that to the lab, and that is experimental. And then study the physical and mechanical properties which take place in layer of rock and the effect of the mining process. So sometimes you would have, just like this bottle has got some distinct lines around it, you can have an excavated surface that has got these distinct layers. It is your duty again to see how is each of these layers, okay, different from the other? So if I have layer 1, it will have different behavior, different conditions and all that. When you go to layer 2, it will differ. So condition of a particular side of the pit will be different from another side of the pit if it is having this behavior. And so it is our duty to do certain experiments on each of these layers of the rock and make decision. And then the next one is theoretical. Here, this is where you then come to the classroom. Oh, Hook and Brown wrote a paper in 1992. They said that the rock has this behavior, whatnot. And then they applied this mathematical principle, and then they got this. So you are now using these inferred ideas, the knowledge that is scattered in literature. You bring them all together to make sense and interpret that or transfer that knowledge into your flow. So you can go the theoretical approach. And again, you want to find out, we were told to use, let's say, rock science, one of the rock science packages. We used it and we are getting a factor of safety of 1. We tried Flag 3D and we are getting a factor of safety of 1.2. What is different about this? How is this going to affect your decision making? You will then be interested in finding out the underlying principles upon which the software works. That will help you to decipher whether that 0.2 is relevant for you to relax and say, oh, once they say factor of safety is 1, that's where I have problem. But of course, I have 1.2. So I think I can take watch it. But then, the moment you are able to find the underlying differences, the principles upon which and the assumptions they used in designing that software, and that will stem from the maths that you have studied, and that is the theory we are talking about. So we move on to the next phase. It is getting interesting gradually. Any questions so far? Okay, nice one. So indexing. What is index property? Index property here is a system that is in place to help us find out, based on certain key things, okay? They are more like properties that we have, okay? A naming system that is available for us to test one by one, parameters that are available to us, which we can take one by one. And depending on a particular project we want to undertake using our rock or the soil, we then say, okay, based on this project we want to undertake, maybe I want to create a platform. And then your manager tells you, we want to move our mine planning office or our technical services office to this side of the mine. So at that moment, we need to carry soil, transport soil to that place, get some rock samples to that place, prepare the land, overlay it with soil, and then place our machines. So based on the type of load you'll be dealing with, it will inform the type of soil you'll be interested in the load and haul team bringing to that site. So what am I preparing the place for? The moment I get to know what I want to do, the next thing will be then, what should I look out for? And those parameters of the soil that or the rock that you'll be interested in to help you make that informed decision is what we term as the index properties. Okay, they help us to describe, oh, our soil is quite damp, our rock is porous, the permeability of our rock is quite high. And so if we use it for this place, since there's a hill here, there's the likelihood of water flowing over onto that platform. And when they get here, they cannot flow if the permeability is so high or low. The water cannot flow. It means it is going to settle at that particular place for a long time before it drains off. So no, we don't want that type of rock material or soil. So please, let's change the type of material. This is why you want to know the various properties. So indexing is important, which will help us describe and quantify rock properties or soil properties. Accuracy, let's carry on.
From what you are saying, meaning the index is a form of indicator which let us understand the behavior and also the performance or the quality of the rocks. So
Exactly.
is it different? So what is it different from the strength properties of the rock?
No, so as part of these things, we will get to the strength. The strength things are talking about the mechanical. And then these ones are more like physical indicators that we can use to judge. So it's just like every human being. You have got certain features. As soon as someone hears or sees your demeanor or something, they can tell your mood. They can tell who you are and all of those things. That is the type we are talking about here as indicators or the index.
Okay.
Are we okay?
Yes, sir.
Crazy?
Yes, sir. I'm okay.
Good. So let's look at this slide. So rock exhibits vast range of properties, various properties, which reflect vast variety of structures, and then fabric. And fabric here we are referring to the arrangement of the various elements, which we have mentioned a couple of them already, okay, that make up a particular rock type. Then the rock in its natural, okay, rock is natural. That point has been established already, okay? And since it is natural, it is going to come with several features, several properties and parameters, which we have to bring all of these together one by one, one by one, one by one. And when they all come together, that's where they will then make sense to us. So the performance of the rock under the action of load, water, temperature, and certain tectonics of the earth depends upon the physical and the mechanical properties of the rock material. So how your rock is going to behave when the load is applied on it depends on the physical nature of that rock and then the mechanical nature. And the mechanical nature here is more about the strength components of the rock. That is more like when I exert force on it, what will happen? So it's like you are intentionally exerting certain amount of load on it to see how it is going to happen. And then the physical one is just like, observing it to see. And then maybe using that as a criteria to slash certain things off even before you start the serious business. So let's move on. These are all things that define the properties of a given rock material. There are many. And so we'll pick them one at a time and describe where there's calculation, we do them and go along. So we are categorizing them into physical and then mechanical. So we are starting with the physical properties. So the physical properties, okay, are the properties exhibited by rock as a result of its inherent characteristics. So physical means they are more like inborn. They are inborn of the rock. So I see you and I know you are fair, you are dark. These are things I don't need to conduct a test to see. I fetch or pick rock samples and they are wet. I can easily tell that they are wet. So these are certain things we term as the physical property. So depending on characteristics of how they were bonded. Okay, the rocks can be classified as being hard, soft, or loose. So the type of bonding that exists between them can let us identify whether they are hard, they are soft, or they are loose. Then we have the physical ones. So you saw that long chain of the properties of rock generally. And then now we have divided them by looking at physical, okay? And then we will look at the mechanical part of it. So the physical properties stem from the mineralogical composition, okay? We are looking at this, the specific gravity, all through to electrical properties, which we shall pick one at a time and talk about. So the very first physical property we want to talk about is what we term as moisture content. In other books, it is termed as water content, okay? Moisture content or water content. What is it then? So water content here, we are interested in finding out with this rock material Engineer Tuari brought to the lab, how much water is inside the sample? So the amount of water that is present in a particular rock sample is what we term as moisture content. So when we pick the sample and then we are able to determine the water, the amount of water that exists in it, we term that as the moisture content, and it is expressed in percentage. So it is the ratio of the volume of water to the bulk volume of the material. So bulk volume is if you brought a material, okay? Let me put this in here and cover it up. So assuming you brought this to the lab for us to test, this is the sample you brought. So this is the bulk. So if I go ahead and calculate the volume of it, the mass of it, I am calculating mass, okay, bulk mass of the sample, bulk volume of the sample. So the bulk here is referring to the whole sample as it is without doing anything to it. That is it. But then the moment you brought it, we decide to subject this material to, let's say, heat. And then we are able to realize that this black thing is the water, the quantity of water present. As soon as it goes out, whatever is left is now the actual solid. So here in the technical terms, we call it dry mass of the sample. If I add the water together from the field, what is this? Bulk. If I take the water out as the black substance and it's left with the solid one alone, which I know there is no water, it becomes dry. So what is happening here is that you are looking for the ratio of how much. So now you take this water and weigh. What was the mass of this? Or what is the volume of this substance? Once you know its volume and you divide it by how much the volume was when they brought the entire sample to the lab, the ratio of that is what we term as water content. Then we have another thing called specific gravity. Specific gravity is more like it's a measuring tool that helps us to determine how heavy something is in relation to water. So I want to determine how heavy this mouse is relative to the weight of water. So the assumption here is that water is a standard material that we know it doesn't change at a particular temperature irrespective of your location in the world. And so we are using it as a relative or a measuring tool, knowing its mass. We want to now compare all other material to it. And so the moment I get to know that this material is, let's say, and we know the mass or the density of water is 1 grams per centimeters cube. So the moment I pick any other material and I know the density of that material to, let's say, it is 3, already I can say, oh, this is heavier than water. So the moment I put it inside water, it will sink. So specific gravity helps us to determine the relative difference or how heavy a substance is. And how do I get that? I need the weight of that substance. And the moment we say weight, it means we are considering acceleration due to gravity as an element here. So the weight of the substance over the weight of an equal volume of water. And that gives us what we term as specific gravity. And it's the same thing we are using this bottle of water to determine. So if I have the density of an object over the density of water, again, I am getting specific gravity. Then we have another. Hello?
In specific gravity, why do we ignore the pore spaces?
The pore spaces. You are looking
Like
at density. If you are using the volume of water, okay, the weight of water, or you are using the density of water, depending on whether you are using bulk material, the pore spaces are present. So we are looking at density, and density sometimes could either be the dry density or the bulk density. So it doesn't specify whether you are using with pore spaces or no pore spaces. That's what's happening here. Yeah, Richard, your hand is up.
Yeah, Doc, you made mention of the density and where the mass, you made mention of it that the specific gravity, we use the weight. But I know from the various lab measurements or the in-house specific gravity we do, we rather use the mass. We don't use the weight.
So I said you can use the weight, and when you are using the weight, it means you are incorporating acceleration due to gravity.
Okay.
I emphasized that. Are we clear?
Well noted.
Good.
Well noted.
Then we have another thing called, is your hand still up? Okay. Density. What is density? In simple terms, we have been saying it is the mass per unit volume of a substance. But what is it? Okay, let us try to see if we can make it quite simple and self-explanatory. Density is just interested in how packed. So assuming I pick this box again, and assuming this box is filled with sand or it's a rock type, I want to find out how packed this particular substance is in terms of the various packing, the packing behavior, okay? So it means if I cook 1 cup of rice and then I ask a friend to come and just fetch a ladle, depending on the amount of pressure the fellow will use on the ladle against the saucepan, the quantity of rice will vary from another person's ladle he or she is going to fetch. And so we are looking at the packing behavior of the tiny particles or the individual particles that made up a particular substance. And I want to know the solids part of it as against the volume of that substance, okay? The mass of that packed material as against its volume. If the volume is less and then the mass is more, I'm going to have it more or less signifies that your substance you are talking about is highly packed in terms of the particles that are present. It means mass is more than volume. But where you divide and then you are getting fractions and all that, it means the substance is less packed. So let's look at that. In the definition, just as we know it already, the mass on the volume, the unit volume of the substance, is what we are still using. The definition has not changed. So the types of densities that we have: green, bulk, saturated, and dry. I want to add the dry to it. So I'll pick them one at a time and explain. So I am starting from what I know you will know. Okay? From there, we get to the others. So let us start from the dry. When we say dry density, waiting be that. So using the same analogy, I have this. The black substance in here is water as usual. It hasn't changed. And then this is a container, which is a rock sample Mr. Kosa brought to us to test for him. Okay? When you bring the sample, and I want to know the density of this substance, if I don't do anything to it, just as fresh as he brought them in the sealed rubbers, I just go ahead. Oh, what is the mass of this box? I didn't do anything. Oh, what is the mass? I just weigh. Pick my tape and check what is the volume of it, the length, and then the breadth of this box, and then the height. I calculate and I get my volume. If I divide that mass by the volume I have gotten, fresh substance, it is bulk density. Bulk density is what I have found. Then, after doing that, I say, no. The young man said he needed to find out how much water is present in this substance. So I place this in an oven, usually at 105 degrees Celsius. Once I place it inside the oven, after a while, mostly 24 hours, if I take that substance out and then place it on the scale again, what do you think will change? Anyone?
So the weight will change.
Thank you. So that mass will change. It will become less because when I placed it in the oven, the water was no more. So now it's left with the solid without the water. But remember, there is never an empty space without something. Who will help me out here?
When the water leaves air.
Air. So as soon as the water goes away, air takes that place. So I know now my substance is dry because there is no water. Then I go ahead and check the volume of that particular substance. When I do that, and this volume is coming from the earlier one, the bulk one, okay? So if I divide that, I am looking at what we term as what? Dry density. So now we have dry density where there is no water. Bulk density, the fresh substance with all the things we think are present there, they are there. And I go ahead, check the mass, divide by its volume. That's bulk density. Place in an oven, take away the water, leaving the sample like that. I check the mass, the new mass, without the water, that is dry mass. Divide by the volume, that is dry density. Then we have what we call saturated density. That one, when the young man brought the substance to the lab, I just intentionally soak the substance in distilled water for over days, to an extent that I know very well there is no other room available for water to get into the substance. And I decide to check its mass, check the volume, And then that result I get is saturated density. So saturated simply means ensuring that your substance is soaked with fluid, a particular fluid, such that it has no more room to take in any other fluid. When you check the mass of that soaked substance over its volume, you are checking what we call saturated density. Then we have grain density. Grain is after you took away the water. Remember, you mentioned something was present. What is that?
Water.
Air.
Air. So you are going to treat the substance such that you are doing away with the air in it, and what will be left? Just the solid particles only over its volume. Then you are looking at grain density. Okay, so here you say mineral aggregate per volume of solid material. So here you now have the dry substance, and then you just check the volume of the actual solid. So it's just like you crushing the material to now check its volume without all the air voids or something. You are doing away with all the empty spaces that are present to check the exact volume of the grains only. Then you are looking at grain density. So these are the various densities that are present when you are talking about, depending on whatever project you want to do. You may be interested in finding out just density of a material. You are good to go. You may want to use the material for something where it should be dry. And so you want to find out what is the water that is pre-existing in the substance. So you check your water content. And then now see, if where I am going to use this material for my project is already a waterlogged area, then I don't expect that you bring me a substance that already has about 50% water inside it. No, I wouldn't be happy with that substance. So that's why we go ahead to work on some of these parameters or physical properties of the substance. So the International Association of Engineering Geology came up with a table that is helping us classify and describe by words the various types of material. So we have class 1 to 5. So if I have a material that has dry density, it means without water, it has a density greater than 2.7 grams per meters cube. Okay. Then this type of material I am looking at, I'll say it is class 5 material, and I will describe it as having a very high density. Then when your material has a high density, it is a trade-off. It means it is having less empty spaces, which will mean there won't be so much void spaces inside that substance. So you have lower porosity, which is also a physical property we shall describe very soon. And we have class 5 all the way to class 1. So the class 1 is where you have your dry density very low. After taking away your water and checking the mass divided by volume of your substance, the akayeketuebi. So once you have that, you say your density is low. And then when it is like that, the trade-off is that you are going to have more empty spaces inside the sample, which will lead to a very high porosity value of over 30%. And we are mining engineers. When our porosities are high, we don't like that. But if you are a petroleum engineer with us, if your porosity is high, you will be happy. Why? Because you are interested in oil. And you being interested in oil, you expect that your rock should have empty spaces that are highly connected, such that oil can flow through that material and sometimes even contain the oil. then you say afapapa. But in a mining engineer, we got nothing to do with porosity, high porosity values. We don't want them. We prefer this side of the table. And this top, no, we don't. We are not happy with that. So let's use this here. Assuming you are preparing a whole road, and then you go and pick material. What type of material is likely going to have high porosity? Sedimentary material. I don't think you will go and fetch sedimentary materials, much of it, and come and say you are using to create your whole road. What do you think will happen if your dump truck, your cat 777 passes by, or 785 passes by? Just one walkover or passover on that material, and then your whole thing is flat. And you have to start refilling. So we don't want these things there. Then we proceed. So density is used in various places. And as such, we can also use another medium to determine density of a material. If we know the temperature of, okay, we want to determine the density of a material at a particular temperature, it is also possible. All we need to know is to determine the coefficient of expansion that exists when there's contraction and, okay, expansion and contraction within the material, okay, and it conducts heat and it begins to contract. We want to measure that difference that is always existing there, and that is the coefficient of expansion, okay, of the rock. If we get to know that, that is what we are putting here. Then now, what is the density of the rock when the temperature was 0? We know that. When the temperature began to rise to say 30%, what is happening to the rock? If we are able to determine the coefficient of expansion at that 30, then we can easily determine the density of the material at 30. Are we fine? Good. So we move on. So mass density, we know and have established already that density is such that it is one of the key things we use in determining the specific gravity of substances like our rock, the various types of rocks. And so water already has this density. Yes, this density, mass density of it being 1,000 kilograms per meters cube or 1 grams per centimeters cube as the standard units for density of water. Okay, so the moment you know this specific, okay, the specific gravity of, yes, Nyako.
Yeah, Doc. Looking at the table provided, the shale mass density compared to that of the granite, the shale has 2.75, the granite has 2.65. I was expecting that of the granite to be higher than that of the shale because of the granite, as you know, is of
being highly
igneous.
compacted. Yes.
Exactly.
Okay, so so maybe this could be an error, but if you can check that for me slightly now, can you?
So I'll go online and check and get back.
And then get back to me.
Okay, Doc.
So assuming you have the specific gravities of various elements, okay, if you have specific gravities of various elements, you can easily multiply, because we said that if I have the mass, the density of a particular substance, okay, let's say density of a substance called T over the density of another substance, which is water here, that's the standard medium. It is giving us something we call specific gravity, okay? So assuming I have something here called the specific gravity. So knowing these two things, the SG of this T is going to be you knowing this density of the T over the density of water. This ratio is what gives you what we term as what? The specific gravity of that particular substance called T. So it means that in the future, if I have any element, the T, if I see it somewhere where I am not giving its mass at all, but then I know that the standard unit, okay, I know that, okay, the answer is seen. So if I know that the density of water remains the same as 1,000 kilograms per meters cube, it never changes, then what will happen if I need the mass of a substance? Because I already know the Sj of T, all I do is just multiply, and then it gives me the density, which is what we are terming as the mass density of that particular substance. So it is the same thing we are trying to do here. So if I have an element like sandstone, 2.2, okay, if I have an element like 2.2 as the specific gravity, and I want to know, so it means these two are interchanged. So it is shale rather 6.5 and this being 7 like this. So if I have an element having Sg being equal to 2.2, and I know that the density of water is 1,000, and I know that Sg is equal to the mass density of that substance, okay, assuming that substance is let's say T or X. X is very familiar when we are doing these calculations. And I have the density of water, W. This is the formula. So if I know just this, what do I need to do? All I do is just cross multiply. And I have Sg times water is equal to density of the substance X. And that is exactly what we are doing here. It is the same thing we are doing here for an element called unit weight. Usually I tell students not to bother themselves so much. Just understand unit weight as another form of density. But the only difference is that you are considering the acceleration due to gravity that is being exerted on the substance. And so it's like you having the mass of a substance. The moment you multiply that by acceleration due to gravity, it changes to what we term as what? Weight. And so if I want to know the weight of a substance, the unit weight of a substance, dividing this weight, if it's the weight of a substance, by its volume is what we term as the unit weight. And this thing is used often in the construction field to check the material they move around. And so with that one too, we can easily compute, which is the same thing repeating here. Okay, so if I have the unit weight of the substance, I can ease the specific gravity of the substance. All I need is to multiply it by the standard unit weight of water, which is a constant here. So the same principle we used for the Sj approach is the same thing we are using here. And then we get these correspondent values for them. So the higher your Sg value, the heavier you are in relation to, or when we compare you with water. Then our next thing is porosity. What is porosity? Porosity. Porosity. Porosity is also another physical property that seeks to find out how much empty spaces are present. So you just want to quantify. Let's use this bread. You see, when you buy a loaf of bread, they add yeast to it to create that loaf of bread for you. So you realize that there are empty spaces. So just take this box, for example. There's an element in it, and this element has got several, it didn't fill the box up. There are empty spaces all over. And assuming you have to quantify the actual portion of the soil or the rock, that is the particles themselves. You take them out and then now see what is the volume of this bulk material previously and what is the volume of the solid space, the solid material itself. You determine that. And then dividing that by the bulk volume you already got, you are getting what we call porosity. So porosity is the volume of the empty spaces over the volume of the bulk material. So if I buy a loaf of bread, and assuming I were to squeeze that loaf of bread, what have I done? I have tried taking away all the empty spaces that is giving that bread the fat look. The air is gone. Now, what is the volume of that squeezed bread I now have? Which is actually what is going to satisfy me. If I squeeze it and check the volume of it, okay, that volume I have gotten is the solid. When I bought it at fresh from the shop, that big thing I was looking at is the bulk volume. When I squeeze and then now check the new volume of the substance and subtract the difference, the air. So which one do you think will be bigger here using the bread analogy? Which of the volumes is going to be bigger? Is it the air or the solids?
Of the air.
Thank you. Because you have a loaf of bread as big as this. After purchasing it, you check the volume of it. The length times breadth times height. Oh, I know the volume of this butter bread. Now I begin to squeeze it such that all the air should go out, leaving the particles that make up what we call bread. Then I check the new volume I have gotten. The difference is the volume of the air or the pore spaces, the empty spaces, divided by the initial volume I got when I bought the bread from the shop. That is what you have here. When you express it as a percentage, you are looking at porosity. So in the same way, our rock also has empty spaces. So we can easily determine the solids that are present there and then the empty spaces that are present there. When we want to quantify the two and we realize that the empty spaces are more, there's no way you would be told to make a whole road and you go and fetch that material with the very high porosity values for your filling. No, you wouldn't do that. But rather you'll be looking for solid materials, materials that have less porosity for that particular activity. Then we move on. So porosity can be described as highly porous. So when I have a material, okay, that have clearance of greater than 0.1 millimeters, okay, so I'm looking at the empty spaces that exist within these substances. If they are greater than 0.1 millimeter in terms of their sizes, their clearance that exists within them. So the clearance here is, if I have a material where at the end of the day, I see one pore here, and then I see another as that wide, okay, all over the substance, then the material is going to be highly porous. But then if I have one that is between this range, I say it is porous. And then when they are closer, the spaces are quite closer to each other, such that you even find it difficult to tell which one is a hole and where is the next hole. then I am looking at what we term as non-porous material. Of course, every material may have that tendency. It is there, but it might be negligible.
So, Prof, please,
Yeah.
so why not less porous but non-porous? Because you are talking about the presence of the pore spaces, but it's negligible.
Yes, so this is what theory has for us, that we should call it as non-porous, because when you have this and you want a sample like that, and assuming you want water to pass through it to the next, you can stay days and the fluid will not be moving. And so it is equal to it not being there at all. So if you try to measure this particular millimeter nankasa or to say, and then you go in 0.002 millimeters less, it becomes difficult. And so it's just like it doesn't exist. I don't know if I've been able to clear that.
So, Doc, are you talking about their wideness or how small the porous is?
Yes, the clearance they give, okay, in terms of
The
the hole,
interval.
yes, the various tiny particles or the holes that they are giving you to serve as the holes or the empty spaces. Okay. Then we have something we call absolute porosity and effective porosity. In other fields, they are interested in finding out. You know, we have pore spaces on the surfaces of our skin. True or false?
True.
Thank you. But do we see blood coming out of it?
No.
sir.
No. So you not seeing blood coming out of it simply means that the pore spaces that are there are not connected to the vessels or the areas where blood is stored. Is this clear?
Exactly.
That is why
Crystal
you don't
clear.
see good. That's why you don't see the blood coming out. So in the same way, I might have a rock that has empty spaces all over. But these empty spaces, obia sinisibre, every one of them is different from the other, such that they are not connected. So I may see a hole here, see another one here, have water stored here, but the water never gets to this side. Why? Because the hole here is not connected to the hole that I see at where the water is stored. So during the study, when I want to look at porosity, and I'm interested in, is the rock having empty spaces? Yes. Is my skin having empty spaces? Yes. Then that is absolute porosity. The fact that you have empty spaces inside you, that's absolute. But then I am interested in how much of the empty spaces are connected to each other, such that it can transfer fluid from one point to the other. If I can quantify those points that are connected, then I'm looking at what? Effective porosity. Hello.
Go ahead,
Perfect
Doc.
explanation.
Please,
Good.
Doc, can you come again on the effective porosity?
Effective porosity. So to get effective porosity, let's go to absolute again. Absolute porosity, okay? What is porosity? We are saying it is a measure of empty spaces that are present inside a rock sample. Understood?
Yes, sir.
Thank you.
Yes, Doc.
Then now, I want to find out the fact that you have empty spaces, okay? That is absolute. So I don't care whether one hole, and I gave an analogy that assuming I have a pore space here, and there's another one at the back of the box, and I have water stored here, we are expecting that the fact that I can see a hole we would be interested or we would want to know that the fact that there's an empty space here and there's one at the far end, then the water should be flowing from that hole to the back side. But then you see that the water is still sitting at where it is. No movement.
No permeability.
But the rock has empty spaces. It simply means these empty spaces you see are not connected to each other. And maybe the ones that are connected to each other, that is not where the water is sitting. So you don't have water flowing. So if you have empty spaces on you, then I am looking at absolute porosity. I don't care whether one hole is connected to the other or not, absolute. But where the holes are connected, and I just decided, oh, all the holes inside this rock sample, come, let's have some assembly and have a discussion. The holes come up and they are 5. Out of the 5 holes, I realized that hole 1 is connected to hole 4 and again connected to hole 2. So how many of the holes are connected?
3.
3. So with these 3 holes connected, I want to quantify just the connected holes alone. Then that is effective porosity.
Okay.
Are we okay?
Doc, please, I have a question.
Yes, carry on.
Please, I want to understand why practically, I mean, in the application on field, why we would want to determine absolute porosity and effective porosity.
So in the field as mining engineers, we want to know, is the rock porous? If the rock is porous, we will go further to do a certain study, which we call permeability, to find out how permeable our rock is.
Yes.
If it is highly permeable, it means it is going to allow the flow of water. And what is going to cause the flow of water? It is the connectivity between one hole to the other that will allow the flow of the water. So if your effective porosity is high on a rock material, then it means your tendency of having high permeability is also going to be the case. Please, are you okay?
Yes, thank you very
Thank
much.
you. Then,
And
Mr.
Doc,
Costa, your hand is up.
Doc, so
Yeah.
in this case, that means it wouldn't be a good material to be used for filling.
Thank you. So it's just like you having a yes. So if you have material that is highly porous and you take them to a place to do filling,
Like sandy soil.
yes, like sandy soil, then you have to keep piling and piling and piling and piling, because the moment you put it down, the water comes to the top. You put it again, the water comes to the top. That's what will be happening.
So, sir, what I want to know is that what if they are, I mean, like the whole style you were talking, because you were mapping, you first said you were mapping like, let's say hole 1 to hole 4, and then to, let's say, hole 2. But what if they are opposites and they link together? Is that too effective porosity?
So long as the holes are connected and they can allow the flow of fluids, that's effective porosity. If they are connected but they don't link to each other such that flow is possible, then you cannot have effective porosity. So the effective porosity here is highly used in the area of petroleum, where they want oil. So they want to quantify what portion of this sedimentary material has got its holes connected, such that if it is the medium through which our oil can be obtained, we are going to have high quantities of the oil. Are we okay there? Mr. Kwasa?
Yes, sir.
Good. So in your case too, as a miner, you are also interested in finding out, because I've mentioned as a geotech officer, your number 1 enemy is water. So you are doing this testing to be sure that your rock has the tendency of giving you trouble. assuming you have a nearby stream somewhere and your material is highly porous, and the fact that it is porous does not mean, so this is the analogy here. The fact that something is porous doesn't mean it will always transmit flow. So once you know that it is porous and it is highly connected, then you should be thinking of buying more pumps, more pipes to deal with your water, because you can have your surface water or that stream finding its way into your pit all the time, and you will deprive your community with water and they will start coming at you. Yeah, I can see your hand was up.
Yeah, so as you rightly said, as a miner, so within the pit, you see, with this porosity, when you get to some section or some pieces of the walls, you can easily see that the water want to flow, but since they are not connected, it's not able to flow. So as a geotech team, you go in and have something they call the field post, meaning they will drill through the walls they will drill through the walls so that the water within that section or portion will really flow out of the walls so that the walls will be stable.
Thank you very much for that addition. Well done. So this is it. So we have compaction and cementation will help decrease porosity, whilst fracturing and other chemical reactions that may exist in any substance can also help increase porosity. So we can have primary porosity and then secondary. Primary porosity is when the rock or that material was formed in its original location. Were there empty spaces in there? If there are empty spaces that existed when the material was formed, that's at birth. That is primary porosity. Then as a miner, you went there and did certain excavation, exhumed material, scatter, all dislocated all the particles. And then now we have different type of material, but the material sitting there with void spaces. Then that is a secondary porosity you've created. So take it, for example, you are digging a hole, a manhole. Remember, we all have encountered this situation where you dig a hole, you want to put back your material, and then it enters, leaving excess on the side. So at that moment where you have the excess material on the side, what do you think happened? Because you exhumed, you created a lot of void spaces that has been occupied by air. And that's why you can no longer fill that hole you created with the same quantity of sand, unless you do something we call compaction, which we talked about here, with the aim of expelling the excess air that you have introduced. So where you do your excavation or you disturb the material to create the voids, it is secondary porosity you have caused. So this is the picture that's just showing the various pore spaces that exist within a material. So you see, I have empty space from here to there, but then when I come to this center, no connectivity. Then you can also go again here, no connectivity. But then if water can indeed go through this, there should have been some space here, which there is. Then I get here, there is no connection. So we are interested in finding out which sections can permit the flow that's effective. So we have certain porosity that can occur as a result of an individual pouring some chemicals somewhere. Okay, so voids by solution. So you pour some elements. Let's say, for example, you want to mine salt, but you don't want to excavate, and you decide to use hot water, brine. Okay, you want to mine some elements. and then you decide to pour hot water into, okay, hot water with some element inside. That is a solution. It goes in there and it causes the dissolution to create voids, because that thing you have poured in is intentional and it is going to attack a particular element within the solid material. And as it eats into the material you are interested, it's just like you pouring cyanide onto an excavated a pile of material, a heap. What do you think happens? The cyanide goes through the pile like that, trying to eat the gold element within. And then before you know it, it is creating empty spaces within the substance. It's the same thing here. So when I'm using solution to dissolve something, and at the end of the day, it leaves empty spaces within the entire body or that medium, I have created a type of porosity that is called solution porosity. Then we can also have porosity that is caused by fissures, joints, fractures, and other things within the rock material, let's say the discontinuities. Then we have another thing called dolomitization, okay? Me having a limestone that is transformed into another type of element called a dolomite. So limestone changed into a dolomite is dolomitization. And this type of transformation, the type of rock that is formed becomes a metamorphic rock. Okay, so this process will create certain voids, further voids into that substance or that type of rock we are talking of. And that is the chemical equation here. Chemistry for no. Monfanfa taste. Your chemist.
Okay, I'm free.
We are here.
I see Swansea's hand up.
Yes, Doc, please, I wanted to find out, given the definition you gave for the porosity, which is caused by fracture, fissures, and joints, is it not supposed to fall under primary porosity rather than secondary porosity? Given also the definition you gave us for primary porosity.
Okay, so this is more like you talking about certain activities that can lead to porosity. Okay, these are certain things that bring about porosity. And so this joint and fissures and whatnot, if they existed by nature, they become primary. If it is through your excavation that they were caused, you know, you can go and create an excavated surface and then there's a crack. You introduced it. That fissure is now more like, so that fissure you have created or the fracture you have created becomes secondary because it didn't exist before. So any action that is natural, bringing about the empty space within the substance, okay, it is secondary. When it is existing prior to your activity, it becomes primary. So you can classify these as and when.
Okay, so Doc, by definition, this one says it is caused by, I'm reading from the second line of
Okay.
the point B. It says caused by various forms
The
of
load.
Exactly.
diastrophism, such as folding and faulting. Is that not a natural occurrence?
Aha. So it means that the rock structural failure under loads. Okay, the moment you use these things, it means you introduce
Under
the
load. Yes.
Okay. So there's an applied stress.
There's an
somewhat.
applied stress somewhere that is bringing them.
Okay, thank you very much.
Yes.
Yeah, Doc. So I wanted to address the answer you gave him. Fracture, fissures, and joints are all deformational structures which are not inherent in the rock at the time that the rock are formed. Rocks are laid horizontally without any structural defect. It's only as a result of secondary deformational events which will bring about the fracture, fissures, and joints.
Thank you.
It is the reason why they are placed under secondary and not primary.
All right.
Okay, thank you so much.
Thank you. So this is also a table that will help us. So please don't be misled. As a minor, if you have this table, you will be interested in turning it upside down like this. So if it's a petroleum engineer, he sees porosity over 30%, excellent. A miner would turn the table this way. Porosity 0, excellent. I don't know if it's clear here. Hello?
Come again.
Yes, please.
Yeah, no.
Yes. Based on what we are here to study and our application of rock mechanics, porosity is not something that we are interested in as mining engineers. And so if I pick a rock sample and I test and the porosity values are high, because I'm not interested in porosity values, it is the reverse of this table that will apply to me as a miner. And so if I check my porosity values and they are high, it becomes poor. I don't want them, those things. But when I check and porosity values are quite negligible, it is my favorite. So I would say it is excellent for me. That's just the point I'm trying to create. Are you fine here?
Yes, Doc.
Thank you.
Hello, Doc.
Yes.
So meaning for a miner, negligible is excellent, and for a petroleum engineer, excellent is.
Thank you. Thank you. That is exactly the point I'm trying to make. So if you are a miner and you see porosity being so low, you will be very happy because the rock is competent. But if you are a petroleum engineer and you see porosity very high, you will be happy because the higher the porosity, the higher the chances of the various pore spaces being connected to provide you with oil. So you are happy about that.
So, Doc, please. So that means this table is not for miners. This is not.
So this is a standard table that is provided by researchers. So we are looking at it saying that if I have these things being negligible, that will be our favorite part. I don't know if you understand it here. Is it clear, Mike?
Can you come again, please?
I said this is a standard table provided by researchers. Okay, it exists. But then with this classification, based on your application, you will be interested in the negligible and the poor side of this table.
Correct.
Yeah, Doc, please, is it from physical observation or there is a method to which we can use to measure and know it ranges between 0 to 5, 5 to 10 in that order?
Yeah, this one, if you want to measure these things, that is the formula we saw earlier. You picking the sample, measuring the bulk volume of the sample, okay? Going ahead to check the amount of solids that are present in the sample. Deduct that from the bulk volume. The difference is the air, the empty space. So this is actually possible to calculate in the lab. You can do them. So when you are done, you express it as a percentage. So it simply means if I have this rock and I'm dealing with negligible, it means I have 5% of this whole volume of rock having been empty spaces. And so imagine having this whole block of rock and you have 40% of it being empty spaces. That will not be good. You can't use it for any serious job at your workplace. Unless maybe you are done with your road works and you want some smooth material on top. So you go and pick them up to spread. Okay. Let me see something from here. We will finish this now. And tomorrow, God willing, you meet my teaching assistant for calculations on all of this. He will take you through some of these things again to help you do computations on the various parameters, physical properties that we have talked about. That is what you are going to work on with him. And then to solve some example. Once that is clear after him, we are then going to have our first assignment, which you will do and submit. And the next one will be an online test. This one is going to be calculate and submit to me. Okay, so let's see. So
feedback.
Oh, please, can you repeat again? Our network issues. So,
I said tomorrow, God willing,
Redu.
you'll be meeting my teaching assistant who will take you through certain these principles again. He's not going back. He is continuing with you on phase, something we call phase relationship. This volume, the mass, the weight, what are the things, the connections there. You talk about all that and solve some examples. Once you are through with him, the next will be an assignment, which you will work and submit via a platform. So the moment you fail to submit and the portal close, please don't call me. Don't send me WhatsApp. I won't mind. So do the calculation and you forward it through the link I will share with you on your WhatsApp platform. And that's it. Then we will mark and give you your feedback. Okay. So that is it for that particular what is going to happen tomorrow, because tomorrow I'm going for result vetting and I might not be present here. So we have uniformity of grain size. So if I have a sample that has grain sizes that are all uniform, it is going to create certain voids present inside the substance because we are all the same. So it's just like you having rounded pebbles inside a sack. There will be empty spaces that will be created because they are all of the same nature and shape, which cannot be covered, and that will create porosity. Okay, but when they are mixed and they have varying sizes, it can reduce the porosity because some are bigger, some are rounded, some are sharp edges and all that. They all come together, and at the end of the day, they are able to pack very well for you to reduce porosity. So packing can affect porosity values. Particle shapes can affect porosity value. How uniform your grains are can also affect your porosity values. And then the degree of cementation, how the cementation took place. I have particle 1, particle 2 coming together to bond. If they come together, you see, as I have done, if you check carefully, there's a space in between my fingers. So if this is cementation that has taken place already in a rock material, then that degree, how will you describe it? It is not 100%. It is short of some quantity, and so it is not well done. So this degree, this short change in terms of the compaction is going to bring about porosity, either increase it or decrease it, depending on how much success you have with the cementation. And this is also another expression for porosity, and all of these things will be needed. That is the volume of voids over the solids, okay? Is what we term as void ratio. So now what is void ratio? Void ratio, you are just interested in finding out. Now I know these are the empty void, the void space inside the substance, as against the solid, the volume of the solid in the substance. The ratio of it, you want to know which one is more. Is it your air or the solid? So I buy a loaf of bread. Check the volume of the empty spaces, just like we did earlier. What is the volume now? Squeeze it. Take the solid out. The balance that is left is the volume of the voids. Divide that by the solid that you got. If you do it and you are getting 0 point something, it means that your void spaces are quite less as against the solid. But you do it and you are getting larger values, whole numbers. It means your empty spaces surpasses the solids. And those are the things you'll be talking about, God willing, tomorrow after you have looked at this. So tomorrow, God willing, we'll look at soils and porous rocks. What are the relationships that exist amongst these various parameters, physical properties we have talked about? And once we are through, we pick our first assignment. So I will make this material available to you right now on your WhatsApp page, so you can go over it. So tomorrow, God willing, my TA will be starting from this topic. In the absence of any other question for me, I think we have done enough. If I add more at the assembly back, let us close.
Doc,
Doc, my
so
time.
with this scenario, using the bread as an example, then that means that which bread is more porous than
Thank you, Doc.
the
Thank you, Doc.
sugar bread and then the other bread?
Exactly.
Doc,
Yes.